So just as a reminder, I put some notices up on the Google Classroom. I won't go over them here, but do make sure to look at that. They're basically about the timing of some assignments and the timing of the first test, which is going to be on Wednesday. And we may be able to spend a little bit of time reviewing on Monday, but I don't I don't intend to spend like a full class period reviewing for each test. We do need those class periods to do class, but I think you can have a review session with your class tutor. You can have a chance to ask me some questions on Monday for the test. I'll put up some review questions for you, and if you like, I could even put up a like one of the previous year's tests. If you've got a hand on one of my tests or another instructor's test from a previous year, sure, go ahead and use it to study. I don't reuse tests, so no worries there. And I'll put one of the old tests up on the classroom so you can see it. But my opinion on that is that the old tests probably don't help you that much. The thing that's going to help you is studying the section, reviewing the videos, reviewing the sections, and then going over the problems that we've done in class and on homework, and then going back into the chapter and selecting some other problems from the chapter exercises and doing them yourself. If you're comfortable with that, then you're going to have no problem on the test. But definitely get in touch with me for any concerns or anything like that. So roughly speaking, today's content is going to be from section 2.9. So if you watched my video on the formal definition of the limit, then you basically know what's coming. But otherwise, you might want to turn to section 2.9 so that you'll be able to reference the definitions and look at the examples as we're going along. I will teach the class as if you've watched the video, so I won't spend an outsized amount of time talking about what the formal definition is, but I will at least state it for you. And as I mentioned on the classroom, I'll make some bonus problem about the formal definition on the test so that you'll be able to get like some kind of academic reward for studying the material, but it's not an absolute requirement to know this section 2.9 in order to get an A on the test. It's just filling in some gap, telling you what the formal definition of the limit is, so you can feel that calculus is on a firm foundation, and hopefully like help you build up intuition as we start using these limits more and more often when we're talking about derivatives. Okay, so let me at least write down the definition for you. So we've been throwing around this phrase that the limit of function f as x goes to a is equal to L. And there's a definition for you in the textbook earlier in chapter 2 that's kind of like an informal definition. And that informal definition basically says that what this statement means is that if x is close to a, then f of x will be close to L. Maybe f of x could even be equal to L. That's allowed. It doesn't have to be, just has to be close to L. And so how can you formalize that? So here's the formal official definition. And it's kind of a bugbear to students when they see it the first time, but perhaps because it's traditional to use some letters of the Greek alphabet. I don't know why, that's just how it happened. But let's see it. So this is going to be true if the following holds. So if for all epsilon bigger than 0, then there is some positive number delta bigger than 0. So that if the distance from x to a is less than delta, then the distance from f of x to L is less than epsilon. And that's the definition of what it means for the limit of f of x to be equal to L as x goes to a. So you pick an x first, or sorry, you pick your number a first, and then after picking it, you say, well, if it's true that for every number epsilon, there exists a delta, so that whenever the distance from x to a is less than delta, then the distance from f of x to L will be less than epsilon. And you saw me do like a more full explanation of what all this means and with a picture in the video, so go check that out. But for this class, I want to focus on how to show some examples with this and to make sense of it through examples, because it's not necessarily going to make sense on its own, but at least we could do some examples. And I'll just pick these up from the book and try to work through them because I think they're quite good. At least the statements of the examples, if not the explanations. So let's take f of x equals 8x plus 3. And we know from our intuition that, from our intuitive definition of limit, that if I take the limit as x goes to, what do I want to pick? Let's take limit as x goes to 3 of f of x. Well, go ahead and take for a minute. Think to yourself, what is going to be the limit as x goes to 3 of 8x plus 3? So after you've thought for a moment, you're going to think, well, I could just plug that in. 3 times 8 is 24 plus 3. The answer is going to be 27. So certainly for a nice continuous function with no gaps, no jumps, no breaks, no denominator to worry about that's going to be going to 0, it doesn't look like we're going to be seeing any kind of discontinuity that we know. Looks like we can just get this by plugging into this continuous function and getting 27. So let's verify this fact with this definition. And this definition is saying that, like, if someone challenges you with a tolerance, like epsilon could be 1 over 100 or like 1 over 1,000 or something like that. This epsilon is like a range that goes around the number 27. Can you find a range around 3 so that if the distance from x to a is within that range, then 8x plus 3 minus L is going to be less than epsilon. So what I want to do, instead of working with the formal definition first, let's work with some actual numbers. So let's take epsilon equals 1 over 100. So this has to be true for every epsilon no matter what, but that means that in particular it should be true for epsilon equals 1 over 100. And now let's look at the quantity f of x minus L. Let's investigate that quantity. That's going to be the absolute value of 8x plus 3, that's f of x, and then minus L subtracting 27. So this is going to be absolute value of 8x minus 24. And the key that makes all of this work is you want to relate f of x minus L somehow to x minus a. And if you can do that, then you're going to be able to work with this definition successfully. And what I'm seeing jump out at me is maybe I could factor out 8, so I can rewrite this absolute value as 8 times absolute value of x minus 3. And so this is looking good to me. So here's what I'm wanting to do. So I want to find a number delta so that when x minus 3 is less than that number, this quantity is less than 1 over 100. So here's f of x minus L in absolute value. I'm asking for this to be less than 1 over 100. And that gives me an idea, like what if I just looked at this inequality and solved it for absolute value of x minus 3? In other words, just divide both sides by 8. So I get x minus 3 is less than 1 over 800. And so what's that telling me? It's telling me that if x minus 3 is less than 1 over 800, then the distance from f of x to L will be less than 1 over 100, which makes perfect sense because the slope is 8, scales things up by 8. So what I would do is I would say, let me choose delta equal to 1 over 800. So you see the challenge that was given to me was epsilon is equal to 1 over 100 in this case. Can you find a delta such that whenever the distance from x to 3 is less than delta, the distance from f of x to L is less than 1 over 100? Just by looking at that inequality and solving it, it occurs to me that if absolute value of x minus 3 is less than 1 over 800, then it will be true that f of x minus L is less than 1 over 800. And you can even sort of go in reverse and now prove that. You can say, like, choose delta equal to 1 over 800. And now you can say, well, if, so you can say now, if absolute value of x minus 3 is less than 1 over 800, and now you just do everything in reverse, then it will be true that 8 times x minus 3 in absolute value is less than 1 over 100. And therefore, 8x minus 24 is less than 1 over 100, and therefore 8x plus 3 minus 27 is less than 1 over 100. So I was given the challenge that let epsilon be 1 over 100. So can you find a delta such that if my range of x's is within distance delta to 3, does that prove that my y values are always going to be within 100th of 27? And the answer is yes. If you choose delta equals 1 over 800, then this shows that if you have any x value with the distance from x to 3 less than 1 over 800, then the distance from f of x to 27 is going to be 1 over 100. Any questions or comments on that? So this is how we argue with epsilons and deltas. And if I wanted to use the formal definition to prove that the limit of 8x plus 3 is equal to 27, I can't just do it with 1 over 100. I have to make an argument that works for every epsilon, not just a particular one. But the general argument is very much the same. Because if someone says, okay, let me give you a distance, but it's unspecified, it's just some positive number epsilon, it might be 1 over 100, it might be 1 over 1,000, it might be 1 over a billion, whatever. But given some positive number epsilon, representing the distance from which y could be to the limit, how can we find delta? So what you would do is you would go back and you would look at f of x minus L, and so you'd go back and plug everything in and you'd find out that this was 8 times x minus 3, just like before. Always the critical step is trying to compare f of x minus L to x minus a somehow. And you're wanting f of x minus L to be less than this given number epsilon, and you're asking, how small do I have to choose x minus 3 in order for that to happen? Well, you just divide both sides by 8, just like before. You're seeing that as long as x minus 3 is less than epsilon over 8, then f of x minus L will be less than epsilon. So the distance from f of x to L will be less than epsilon. So then what you do is you turn this around, and this gives you an idea to choose delta equal to epsilon over 8. So that's how these proofs work. Given unspecified epsilon, how do you choose delta in terms of epsilon so that whenever the distance from x to a is less than delta, the distance from f of x to L will be less than epsilon? So you find your delta, here we found it, and then you show that it works. So here's the formal proof. Given epsilon bigger than 0, choose delta bigger than epsilon over 8. And then you can just say, well, suppose that the distance from x to a is less than delta. Then you just go through your argument in reverse, just like before. You multiply both sides by 8 to get 8x minus 24 is less than epsilon, and then you'll say 8x plus 3 minus 27 is less than epsilon, which is the same thing, of course, as saying f of x minus L is less than epsilon. So this is how the formal reasoning matches our intuition. This is also the reason why the limit laws exist, because the way mathematics was kind of developed eventually was we figured out what should be the definition of the limit. This is way after Newton. That was in like the mid-1800s. And then people found themselves having to argue like this, write these arguments all the time, but they didn't want to. So they invented the limit laws just so that they could use these rules that if you knew some limits, you'd be able to calculate other ones really quickly without going through this process. So it is possible to use the definition of the limit to then prove the limit laws formally, and then use those limit laws to calculate limits, just like we've been doing in calculus. For this course, I'm going to skip the proofs of the limit laws from this definition. That is something that you would learn in Math 312 in analysis. But I did want to show you the definition of the formal definition of the limit and at least work through some examples. So let me pause. Any questions or comments on anything so far? Let's do some more examples. Let's prove that the limit as x goes to 2 of x squared is equal to 4. So again, this is something that you already know, that if f of x equals x squared, then, excuse me, then the limit as x goes to 2 of f of x. You'll be able to get that just by plugging in 2 squared is equal to 4. So we know that's true because x squared is a continuous function. We know that's true from the limit laws. But let's use now the formal definition of a limit to prove that limit as x goes to 2 of f of x is equal to 4. And so how can we do that? So all these proofs start out the same way. Like you always say, given epsilon bigger than 0. And what you're going to do then is choose your delta. So given epsilon, how do you have to choose delta? I never know how to choose delta initially. So what I always do is I take some scratch work first on a separate sheet and kind of figure out what I want my delta to be. And the way that I do that is I write down what I want first. I want to choose delta so small that f of x minus L is going to be within an absolute value less than epsilon. So I have to write down what's f of x minus L. So what's the thing that I want to be really small? F of x is x squared, and L is 4. You may already be seeing how this is going to work because this is a polynomial that I can factor. And once I get to this point, what's my cornerstone? What am I trying to do? I'm trying to relate this back somehow to x minus a. In this case, a is equal to 2, so I want to relate this somehow to x minus 2. So I can factor this as absolute value of x plus 2 times absolute value of x minus 2. And this is the thing that I want to be less than epsilon. And so you might say, okay, well, let's sort of take a note from the last exercise and divide through by x plus 2. And so then you're going to get that x minus 2 is less than epsilon over absolute value of x. Plus 2. And then you might be tempted to say, well, let's choose delta equals epsilon over x plus 2. But the problem is that that's not a number, right? Like, so epsilon is a number, it's fixed, but here we have x. X is a variable. X is allowed to move around. So how do we handle that? The way, like the best way to do that is to, like at first, let's agree that to like whatever we choose delta, let's choose delta to be less than 1. So whatever the value of delta is, let's make sure that it's less than 1. And if that's the case, then if delta is less than 1, then whenever x minus 2 is less than delta, then the absolute value of x minus 2 would be less than 1. But let's work with that a little bit. So let's rewrite that absolute value equation. That's going to be like minus 1 less than x minus 2 less than 1. Let's add 4 to all three sides to get 3 less than x plus 2 less than less than 4. So if delta is less than 1, then x plus 2 is definitely going to be less than 4 and bigger than 3, and so certainly its absolute value will be less than 4. And I can use that. So I can basically say, if I've got x squared minus 4 equals x plus 2 times x minus 2 is less than epsilon, I can say if initially that delta is less than 1, then I can say that x plus 2 times x minus 2 is going to be less than 4 times x minus 2, no matter what, because absolute value of x plus 2 is going to be less than 4. And then I can say, well, okay, let's make this less than epsilon, because f of x minus L is going to be less than 4 times x minus 2. Let's make that less than epsilon. And so then let's choose x minus 2 to be less than epsilon over 4. Now you can just divide by 4 like you did before. So then the way you would handle that is you might say choose delta to be the minimum of 1 and epsilon over 4. So like if epsilon were a big number, if epsilon were 10, then you would make sure to choose delta less than 1. And I guess if you really, like 1 is not less than 1, so I guess if you really want to be precise, you might say even take delta to be the minimum of 1/2 and epsilon over 4. And then no matter what, it'll be less than 1, so it'll be true that absolute value of x plus 2 is less than 4. And it'll be true that the x plus 2 is less than epsilon over 4. So you do that. That's your scratch work. So you do that, then you say, okay, choose delta to be the minimum of 1/2 and epsilon over 4. And then you can conclude that delta is less than 1 and, well, you can conclude that delta is less than 1 and delta is less than or equal to epsilon over 4. So what you say is that if x minus 2 is less than delta, then x minus 2 is less than 1, so x plus 2 is less than 4 in absolute value, which we worked out before. And then you just go through your argument. So if x minus 2 is less than delta, then f of x minus 4, which is equal to absolute value x plus 2, absolute value x minus 2, it's going to be less than or equal to 4 times x minus 2, and then x minus 2 is less than delta, and delta is less than epsilon over 4, so this will be less than 4 times epsilon over 4 equals epsilon. I know that's a lot of arguing to throw at you. I know that's a lot of arguing to throw at you, but that's how it's done. So any questions or comments on any of that? Check the chat. Okay. Let me give you one to practice. Here's a practice exercise. Let's take f of x equals 2x plus 1. Please show, using the definition of limit, that the limit as x goes to 3 of f of x. So you know that's going to be equal to 3 times 2 is 6 plus 1 is 7. So given f of x equals 2x plus 1, please show, using the definition, that limit as x goes to 3 of f of x equals 7. And the proof is going to be always starting out. Given some fixed number epsilon bigger than 0, can you find a number delta such that if x minus a is less than delta, then f of x minus L is less than epsilon? So find that number delta first by looking at the distance from f of x to L, and then fill in the argument, just like we did before. Let me give you a few minutes to do that, and private message me any questions. Okay, after giving you some time to work, I'll try to share my answers too. For these linear equations, there's a little trick you can do. So given epsilon bigger than 0, you can always choose, I think, delta to just be equal to epsilon divided by the slope, because you just want to cancel out basically the increase in the y values given by the slope. So I think it'll turn out that we can just choose delta equals epsilon over 2. But let's see that in practice. So the way that I do this on my scratch paper, I'm going to investigate f of x minus L. So I'm going to investigate 2x plus 1 minus 7. And so that's equal to, of course, 2x plus, or 2x minus 6. And now this is where my comment comes in, because now you're going to be able to factor out the slope, and you'll get 2 times x minus 3 in absolute value. So this is what's allowing us to relate f of x minus L back to x minus a, in this case, absolute value of x minus 3. And the relationship is, it gets multiplied by the slope. And if you want this to be less than epsilon, then you're going to want to choose delta to be equal to epsilon over 2, because you're wanting x minus 3 to be less than epsilon over 2. So if you choose delta to be epsilon over 2, then whenever x minus 3 is less than delta, it will also be less than epsilon over 2, and therefore your limit condition will be satisfied. So now that was all on scratch paper for your proof that you're writing down, for your explanation that you're writing down on homework or whatever. You say choose delta equals epsilon over 2. And then you go, once you've chosen your delta, you need to show that it works. So you need to verify that if absolute value of x minus 3 is less than delta, then f of x minus L is less than epsilon. So then you can just go straight to doing that. You can say, if it's true that the distance from x to 3 is less than epsilon over 2, then just run through your argument on your scratch work, but in reverse. Then it'll be true that 2x minus 6 is less than epsilon. And then, therefore, it'll be true that 2x plus 1 minus 7 is less than epsilon, which is what was needed. So for any epsilon, excuse me, bigger than 0 that's given to you, for any challenge, for any range of values about 7 that's given to you, can you find a range of values like a radius delta to put around the x's that'll guarantee that whenever the distance from x to delta, x to a is less than delta, the f of x to L is less than epsilon. And in this case, what's happening is when you draw this picture, when you get 2x plus 1, and you get maybe here's x equal to 3, y equal to 7. So given epsilon bigger than 0, so given some range of values, so epsilon's like a radius about 7. What delta do you need to pick? What radius about 3 do you need to pick? Well, you just pick delta equals epsilon over 2. That radius about 3 is just epsilon over 2. And the reason why epsilon over 2 works is because this function just takes your input, stretches it out by 2, shifts it up by 1, but that doesn't make a difference. So since your function is stretching things out by 2, your range of values around x would necessarily have to contract it around 2. So for linear functions, it is more straightforward to do these epsilon delta arguments. For the quadratic function, we had to use this little trick of saying, well, if delta is going to be a small number, let's choose it less than 1. And then that basically makes our other factor, x plus 2 in that example, being less than 4. Maybe I did that arithmetic wrong. Maybe it should have been less than 5. But if x minus 2 is less than 1, then x plus 2 would be less than 5, I guess. But so maybe I should have written 5 instead of 4. But the principle is certainly the same. So any questions or comments on any of that? Okay, so this is a little peek into the window of more modern mathematics, like how to do the formal definitions, how to argue using proofs, using the formal definitions. If you enjoyed that, consider taking Math 312 analysis later on in your career. And if you didn't enjoy it, then think nothing of it other than it was a Midsummer Night's Dream. Okay, so it's Friday. Let's leave 7 minutes early. So I'll see you on Monday, and have a great weekend.
Thank you. You too.
Thank you. You too.
See you.